In this lecture, we will be covering the topic of related rates, and this follows up on our treatment of implicit differentiation, as that will be the primary tool in related rate problems. So let's recall how implicit differentiation worked. The idea is you want to calculate dy dx, but your expression in x and y does not necessarily allow you to solve for y in terms of x. It may be possible, but it may not be. In either case, we can assume y is a function of x and take the derivative of both sides with respect to x using chain rule, and then we'll have an expression that involves dy dx, which we can then solve for. So as an example, we have here y sine of x equals e to the y cosine of x. This defines y as a function of x, but you can't solve for y. In order to get dy dx, implicit differentiation allows us to take that derivative with respect to x of both sides. This first term, we use product rule. So we have the first, y, times the derivative of the second with respect to x. The derivative of sine of x will be cosine of x, plus the second, sine of x, times the derivative of the first with respect to x, which will be dy dx. Similarly, we use product rule on the right. So first, e to the y, times the derivative of the second. Derivative of cosine x with respect to x is negative sine of x, plus the second times the derivative of the first, and we'll need chain rule here. So the outer function is the exponential, the inner function is y. Derivative of the outer function, leaving the inner function alone with respect to y, is just e to the y. Derivative of that y with respect to x is dy dx. And in this case, what we want to do now is solve for our dy dx terms. So if we get all the dy dx terms on the left, all the non-dy dx terms on the right, what we'll have is dy dx. We have a sine of x term, and then we subtract this term from both sides. So we have minus e to the y times cosine of x. On the right-hand side, we still have this e to the y negative sine x, so minus e to the y sine x. And then we subtract this y cosine x from both sides. And we now can solve for dy dx. So this together means dy dx equals that right-hand side minus e to the y times sine of x minus y times cosine of x. And then we divide by this expression in the parentheses, sine of x minus e to the y times cosine of x. And so this is just an example to remind us of how implicit differentiation works. And again, when we're working with related rates, this is going to be our primary tool. So what do we mean when we say related rates? A related rates problem involves two or more quantities that vary with time, and an equation that relates these quantities. So the way to think of this, or we'll talk about it in more generality, but why don't we actually do an example first to see how this works. So the length of a rectangle is half of its width. At what rate is its area increasing if its width is 10 centimeters and is increasing at 1 centimeter per second? So the first thing we want to think of is what are our variables? And in this case, we have a rectangle where its length is half of its width. So if this is its width, then its length is half of that. So we have length and width. And of course, we know the area, A, is length times width, or in this case, w times 1/2 w, or 1/2 w squared. So the key thing to recognize here is that we have defined variables to model the problem and then come up with an equation relating those variables. Now the idea is this width is going to be increasing. So if the width is changing in time, think of it as you start the clock and this rectangle is growing. If the width is growing in time, so is the area. But the key thing to realize is that this governing equation is always true for any time. So what we can do is think about these rates and then think about how we can use implicit differentiation on this equation to get these rates. So look at the problem. Its width is 10 centimeters, so we're told that at a certain instant, like this thing is growing, and the instant we care about is when the width is exactly 10 centimeters. But the width is increasing at this rate of 1/2 centimeter per second. So what the information we're given here, that is a rate of increase in time of the width. And we're asked at what rate is the area increasing, and that is a rate of change of area in time. So given the variables that we defined, area and width, we see these rates are part of the question. And we now use implicit differentiation on this side, on this equation. So differentiate both sides with respect to t. So we come here and say the derivative with respect to t of a is the derivative with respect to t of 1/2 w squared. And the idea here is that both a and w depend on t. So remember, the idea here is that we start the clock and this rectangle is growing in time. Since both a and w depend on t, we can do this implicit differentiation on both sides here. On the left, the derivative of a with respect to t is just by definition dA dt. And on the right, we have a chain rule problem. The outer function, and maybe we can be explicit here, what we have to do on the right is differentiate that 1/2 w squared with respect to w, and then multiply by dwt. That's a direct application of chain rule. So this becomes, using our power rule for this w derivative, 2 comes out front, and we just get w times dw dt. But what we now have is an equation relating the rates of change that we're interested in. And remember, what we're asked for is this rate of change in the area at this particular instant. So we need dA dt at the instant when the width is 10 centimeters and dw dt is 1/2 centimeter per second. So using our formula here, we plug in that w, which is 10, and then that dw dt, which is 1/2, and we get 5. And if you keep track of your units, this is centimeters squared per second. So at that instant, when the width is exactly 10, given this rate at which the width is changing, the area of the rectangle is changing at exactly a rate of 5 centimeters squared per second. So this is the idea, and we can step back from this example and see what the procedure is in general. And it's really 2 steps. First, define your variables, and then establish an equation that relates them. In that previous model, that was our area and width. Those were our variables, and then we had the area equation that related the two. Once you have that equation, you perform implicit differentiation on both sides with respect to t, and that gives you your related rates of change. And then you could say 3 here, answer the question. So that's really the approach that we use for these types of these questions. And let's do some more examples. Here, suppose we have this scenario where we have a boat 30 miles north of an island, and that's sailing north at a certain velocity. Then we have another boat 40 miles east of the same island, and that's sailing west at this velocity. And then we're interested in how the distance between the 2 boats is changing at this moment. So let's model this. So we'll have our island. Then we have boat 1. Boat 1 is 30 miles north of the island. And then we have boat 2, 40 miles east of the island. And we're told something about how they're moving. So it looks like boat 1 is sailing north, so it's actually moving away from the island, and boat 2 is sailing west, so boat 2 is actually sailing towards the island. And we're interested in the distance between them. How is the distance between them changing? You might think of this as a question you'd be interested in if, say, the 2 of them were in contact by radio or walkie-talkie or something, and if they're too far apart, they lose the ability to communicate with one another. Well, it looks like we have kind of a natural setup here. We could call this distance x and this distance y. And if we're trying to decide something about the distance between them, maybe we call that z. But of course, this is a perfect situation to use the Pythagorean Theorem. Since this is a right triangle, we know that x squared plus y squared equals z squared. And so here we've completed the first step of the problem, where we've set up a mathematical model. We've defined variables and then used the Pythagorean Theorem in this case to come up with an equation relating them. So now we want to start talking about the rates. And we can see some of the rates we have. So the first boat is sailing north. That's the change in the position y from the island of boat 1 with respect to time. So that dy dt is 10 miles per hour as the boat is sailing away from the island. For x, well, the boat is actually coming towards the island at 15 miles an hour. So what we have for x we have dx dt in our convention would be minus 15 miles per hour, as it's actually getting closer to the island, going in the negative x direction. And the question, how fast is the distance between the 2 boats changing, that is a question of how this z is changing, dz dt. So take this equation and implicitly differentiate both sides with respect to time. And again, the intuition here is that this is a moving picture. This boat is moving west. This boat is moving north, so x, y, and z are all changing in time. But the right triangle is always preserved, which means this Pythagorean theorem always holds for any time, which gives us a reason to differentiate both sides with respect to time. So we go term by term, and again, x, y, and z are all functions of time. Derivative of the first term. Power rule 2x. So that's the derivative of the outer function. The inner function was a function of t, so times dx dt. For the next term, derivative of the outer function, 2y to the 1, times the derivative of the inner function with respect to t. And then the same sort of thing on the other side. Now again, if you're having trouble seeing what we're doing here, just as an aside, when we calculate that derivative with respect to t of, say, x squared, what we had to do was the derivative of x squared with respect to x times dx dt. That's this term here. That's how we're getting this. And again, the key is to recognize that x, y, and z are all functions of time. Okay, coming back to this, we see that the 2's cancel, and we get dz dt dz dt is equal to 1 over z times the quantity x times dx dt plus y times dy dt. And now that we have the equation relating the rates, the reason we solve for dz dt is because we know that's what we were being asked to solve for. We now come to this instant. So the instant in question, so dz dt at, well, I'll just write instant because there's a lot of, we'll say at the given instant, we start plugging things in. So x, the second boat, was 40 miles away from the island. So we plug 40 in for x. dx dt, we said over here, was minus 15. Y, the distance boat 1 is from the island, 30 miles. And then dy dt was 10. We just need z. Although z wasn't given, we do know that z can be obtained from the Pythagorean theorem. So because z squared is x squared plus y squared, we have z squared at this instant. X was 30, y was 40. And thus, z is the square root of 30 squared plus 40 squared. 30 squared, 900. 40 squared, 1600. That's the square root of 2500, or 50 miles. So that 50 comes in for this z here. And if we work that out, that will be negative 6 miles per hour. Which means at this instant in question, these two boats are actually, the distance between them is shrinking at a rate of 6 miles per hour. Next example. Suppose we have sand being emptied from a hopper. So that's just something that's pouring sand out. And the sand forms a conical pile whose height is always twice its radius. Radius being the radius of the pile's footprint. At what rate is the radius of the pile increasing when its height is 5 feet? So the first thing we need to do, draw the picture. So we have this pile. Conical just means it's in the shape of a cone. And the radius is the radius of its base. And we're told the height is always twice its radius. So this height is 2r. And the volume for a cone is 1/3 pi r squared h. And again, we know the height is always twice the radius, so in this case, this is 1/3 pi r squared times 2r, or 2/3 pi r cubed. So there is our governing equation that relates our variables. We're asked at what rate is the radius of the pile increasing. Well, that's the rate at which r is changing. So we have our variable r here in a rate, and then dv dt will be the other. But we can look at this question and realize sand is being emptied from a hopper at a rate of 10 cubic feet per second. That's the rate at which the volume is changing. So we're given that the volume is changing at this constant rate of 10 cubic feet per second. Now, with that information, we see the two rates that we're concerned with, one for v, one for r. So we need now differentiate both sides implicitly of our expression with respect to t. So we have dv dt, or maybe we'll be more explicit. The derivative with respect to t of v is the derivative with respect to t of 2/3 pi r cubed. On the left, we have dv dt. And on the right, let's be explicit, with chain rule to get that time derivative, we need the derivative of 2/3 pi r cubed dr times dr dt. And again, that is a direct application of the chain rule. This derivative with respect to r, we do power rule. So 3 times 2/3, or 2, pi r squared times dr dt. And we note what we're asked to solve for is the dr dt, so we want to solve for that. So this means dr dt is dv dt times 1/2 pi r squared. And so we now, having finished this implicit differentiation step, we've solved for the rate that we were asked about, and now we answer the question. So we were told that dv dt we know is 10 cubic feet per second, and then we want to answer this at the moment, at the instant, when the height is 5 feet. Well, we have to be a bit careful. This is in terms of the radius. So if the height is 5, we saw that the height was 2r. So we need 2r to be 5, or r to be 5/2. So this means, to answer the question, dr dt, when the height is 5, we plug in here. So dv dt was 10. 1 over 2 pi, and then our r was 5 over 2. So that 5 over 2 is squared. And this simplifies to 4 over 5 pi feet per second, which is approximately 0.266 feet per second. So again, these examples should illustrate these are all the same kind of problem, all the same kind of approach. You need to draw some pictures, make some labels, define some variables. Once you've defined your variables, find relationships between them, like this volume equation. And then recognize that as you run the clock, this equation is always holding, which means you can differentiate both sides with respect to t implicitly to relate the rates of change of the variables. Once you have that, you answer the question. All of these related rates questions can be solved with this same type of approach.